Good afternoon. My name is Jesus del Alamo. I'm the director of the Microsystems Technology Laboratories, and I am delighted to welcome you to the first seminar of our fall MTL Seminar Series. And today we're delighted to welcome Dr. Mukesh Khare from IBM Research. He's vice president at IBM Research, and he drives IBM's worldwide agenda for semiconductor research. He has graduate degrees, including a PhD from Yale University. He joined IBM in 1998. And over the years has been involved in R&D and also in the implementation of several innovative semiconductor technologies such as high-K, metal gate, and FinFETs that have added significant value to IBM and to their industrial partners. At the present time, Dr. Khare leads a team of more than 1,000 researchers worldwide that is charged with redefining the future of computing for next generation workloads, essentially AI, machine learning, and high performance computing. In fact, he championed the formation at Albany in New York, not too far from here, of the AI Hardware Center, which is focused on enabling the next generation of chips and systems for AI to realize its full potential in the long run. Along his career, he has co-authored more than 100 research papers and holds several US and international patents. And he has received the IBM Corporate Award, the Outstanding Technical Achievement Award, and he's also an IBM Distinguished Engineer. And further, he is the chairman of the board of directors of the Semiconductor Research Corporation. So, Mukesh, it's really a pleasure to have you today here. It's a good opportunity for us to thank IBM for supporting our research activities in AI and in many other areas, and in particular for supporting research in AI hardware. And also, now that I know that you're the also with SRC, thank you for the long-term sponsorship of SRC research at MIT.
Absolutely.
Thank you.
Thank you. Thank you, Professor Del Alamo. It's truly an honor to be here today to talk in an inaugural session. And I was also told not only that this is the inaugural season, but this is the first time this room is being used for this lecture series, which is just fantastic. And I'm really enjoying the smell of pizza that I'm not able to eat yet, but don't worry. This is wonderful. Just wonderful to be here and to share what we do in the space of hardware technology. And I'll talk about it. IBM and MIT has been very, very long-term partner. And it's great to be here, look for partnership, and MIT is also a great source of IBM employees. So, you're all welcome to apply. We'll be here, coming back here for internship, recruiting, etc. Just for an introduction, for some of you who may not know, IBM Research is a worldwide organization with 19 locations all over the world in 6 continents. We have 3,000 researchers working on a set of strategies. And as you can see, on top of it, we have about 1,500 you can say postdocs and interns and contractors. So I will say undoubtedly it's the most successful and very powerful research organization in the world. And I'm very proud that we continue to drive frontiers of technology in various areas. And obviously, we are also very successful in getting awards in these very, very prestigious awards here. Some of the things that I want to also talk about, we at IBM Research, we are the #1 in enterprise systems. We really build systems. IBM's, and I'll describe that there was a very big moment this year, earlier last week, where we announced a new system. So we continue to build IBM Z system, power system, storage systems, which are extremely important. And as you can see that 87% of all credit card transactions actually go through IBM Z system. Z stands for zero downtime. And I'll describe that a little bit more on what do we do and how the work that we do at IBM Research and also in partnership with MIT is so important. There's many ones. One another thing that we are very proud of, our patent. It's the 26th year that IBM is the #1 patent company in the world. We're very proud of it. We are very proud of our inventions, and we are very proud of the fact that we are continuing to drive the frontiers of technology here. And clearly, we are now, in addition to all the things on the left side, which is extremely valuable for our business, we are now driving very aggressive agenda in the space of AI. I will describe that a little bit more. In my view, IBM is the only company in the world which can work on AI end to end, all the way from fundamental material science to devices, to chips, to systems, to algorithms, to application. And what we do is we bring all of these expertise together so that at the end we build the best possible AI system, because that's what's the most important thing here. So clearly, we are very focused on AI for business. Our strategy is around hybrid cloud. I will describe that as well. We made a very, very big acquisition this year, towards middle of last year, which got completed this year, which is which is to drive us, propel us in the journey of how we consume compute, which has completely changed in the world now. We are enterprise service business is very important, and at the end of the day, IBM is all about trust, all about security. If you work with IBM, any enterprise, they don't need to worry about all this difficulty about whose data it is. Are you using somebody else's data to generate? No, your data is your data. That's a guarantee if you work with IBM. So security and trust is the underpinning of what we do at IBM. So let's start with the three beautiful ideas. This to me is just the best time to be in the IT industry. There is a confluence of three very beautiful ideas that's happening right now, which is essentially redefining what we call the future of computing. And these are the three beautiful ideas. The beautiful idea around bits from Claude Shannon. This was a great abstraction. We have been riding on that idea for the last 50 years. It has generated tremendous wealth, value, progress in our society. So that idea we know very well. The beautiful idea around neuron, which is not a new idea. This is Santiago Ramon Cajal, a Spanish neuroscientist. He was the first one in around 1900 who actually understood and documented the microstructure of brain. And that's where this whole idea of can we learn from our brain and how can we use the idea of neuron to inspire our computing. And then the idea around qubits, the famous Charlie Bennett, IBMer, who have been trying to understand how can we use the physics, the fundamental understanding of physics and quantum mechanics to essentially build the quantum computer. If we really want to work and simulate and understand nature, nature is not classical, nature is quantum. And if you want to really go, solve those hard natural problems, then you have to build a quantum computer. And this is what we are now with these three pillars of computing. These three beautiful ideas are coming together. And I will describe what is IBM's vision of how these three beautiful ideas will come together that will redefine the future of computing the way we see right now. So let's go to start to understand how we see the industry evolving, how these three ideas coming together going forward. So we'll start with the first idea, which all of you are kind of familiar with, but I will describe it a little bit more on what we are doing at IBM and how we are generating value around it as well. Because this idea is what has been driving our industries. Today's computers, high-performance computers, they continue to use the idea around bits and how we continue to improve performance of, let's call it traditional semiconductor technology. This is as I described, this is the idea. This was purely an abstraction that came out. And how do you represent states? How do you represent binary states? The idea of bits. How do we get value We have been at IBM extremely successful in leveraging the idea around bits, the idea of converting the idea of bits to essentially the most powerful transaction systems in the world. And these are some of the value that the IBM Z system, our hardware, the big iron that we still sell and generate a tremendous value for our business as well as our partners and our customers' business. You can see that it's some of the value that we are putting on the system. It's the first pervasive encryption. It has capability for end-to-end encryption, basically, which is very important considering the challenge that's there right now with the data, privacy, and security. And as you can see, 92 of top 100 banks in the world use our system. So you can imagine the type of encryption and security requirement that we have to meet is astronomical. It's also very important that we can now integrate these systems in cloud, because that's the way industry and society is starting to consume compute. So this system is now also completely integrated into the cloud environment, both public and private cloud. It is enabling the new machine learning and AI during the transaction, for instance. How can you detect fraud while your credit card is still going through approval process? Can you apply some of the technology, some of the techniques that we are developing in these systems as well? So these are some of the statistics which shows that, hey, we got to keep working on improving the capability of these very powerful systems that still drives big part of economy infrastructure for society. IBM, as you know, has been working in this area for a long time. We had many inventions in this space, all the way that I started my career around 180 nanometer. I'm sure some of you started a little bit earlier than that. And I've been seeing this progress, node after node after node. Yes, this train is hard. This train is not moving as fast as we would like it to be, but this train is still moving. And I will continue to, and I'll seek help from this community here, that we continue to figure out how can we get more and more value, knowing that this one idea is still there. It has significant investment, and what's next in our pipeline. To show some of the investment and the kind of work that we are doing in this space, as some of you may not be familiar with, this is the Center for Semiconductor Research that we use. It's in Albany. It's in collaboration with New York State. It, in my view, undoubtedly, the most advanced semiconductor R&D facility for collaboration in the whole world. Please come and visit us and see the capability that we have. Right now, we are working on developing 2 nanometer technology in this facility. And this facility can do fully integrated processing of wafers from the silicon wafer that you start to actually finish with essentially with working functional devices, functional transistors, or arrays and chips. So that's a fantastic capability. It's very close to Boston, Massachusetts. Actually, I started this morning and drove to MIT. So this is a facility that we should be leveraging and figuring out, how can we keep pushing the state of the art. This facility has about 100,000 square feet of clean room space, basically, for us to essentially perform collaborative research. That's pretty much the job there. Some of the innovations that came out of IBM research, copper interconnect, SOI technology, embedded DRAM, high-K metal gate. What's next? FinFET. Several of you worked on FinFET technology. IBM in our neighborhood here is the only company in the world who actually put together an SOI FinFET technology with embedded DRAM. There is no such technology that exists. This is the most powerful technology, I will say, that was ever created. And this was right here, in our also backyard. And there's several innovations that are included in this technology, which are, as a physicist, the ideal FinFET structure is an SOI FinFET structure, because you don't want to dope junction and create isolation. And you'll find that sometime IBM continues to pursue a path which which is an ideal path, And we keep driving that agenda because at the end, what we are looking for, as I will describe to you, the performance that is highest in the world, the reliability that's highest in the world, because the systems that we build are very expensive and they have certain very high expectation of performance and reliabilities as well. So it's an SOI FinFET technology manufactured in New York for IBM product. It's used in our 14 nanometer systems. There are many innovations included in this. One of the main innovation I will say is that at IBM, we worked on high-K metal gate technology. We introduced gate first high-K metal gate technology. Then we combined that with replacement gate metal technology. And we are the only company we were able to combine both and figure out how can we make the best use of knowledge from gate first and gate last and create really ideal solutions so that the threshold voltage that you need for SOI FinFET device where you don't want to dope your channel, how can you get all of those characteristics just by adjusting the work function from the gate stack itself. This is the most proud announcement that we made very recently, essentially last week. This is the IBM Z15 mainframe-based mainframe. This is essentially world's most reliable, scalable, and secure bits system. I'm still at the bits. I'll move on to Neuron very soon. But that's why bits are so important, that it's actually this system is able to do 19 billion encrypted transactions a day for the mission-critical workloads. Yes, there is a lot of excitement about using public cloud, et cetera, but I will say 80% of the mission-critical workload has not moved to cloud because there is a lot of concern about how, reliability, security. There are a lot of applications that were already written that you can't just move into the new world. This system can run 2.4 million Docker containers on a single system. Now you can start to see that how this system is getting integrated in the cloud environment where we are using, the Kubernetes-based.
What's a Docker container?
Docker container is orchestration of how you package your application. And Docker is a company that has created that standard that we are using in the cloud environment, basically. Now this system has a 7-9 availability. That means it can be off by 3 seconds of downtime a year. So you can imagine that is the type of reliability that is required, and that's why we as a society and IBM as a company need to continue to invest in the bits part of the technology as well. Power 9 is the microprocessor that is for another line of investment that we have. We have a Z line, which is the highest line of systems. The second line is the power line, power microprocessors. As you can see, there is a very significant investment towards making sure that these microprocessors are performing to the standards that we need for IBM's product. Going beyond that, 7 nanometer technology, we announced world's first 7 nanometer test chip in 2015. Right here, this entire test chip was put together in Albany, New York, and it's fully integrated test chip with sub 50 nanometer gate pitch using one of the most important things we introduced here is use of EUV lithography technology. And we have the first EUV tool was Alpha tool that was here in Albany Center where we did earlier work, and then we got our first early manufacturing tool in 2015 timeframe, and we've been working on using that. And this technology, the way we defined was introducing or making use of EUV technology so that we don't have to go through the multiple patterning lithography that generally gets used for these advanced feature sizes. So to give you an example, these are very complex. If you get to go visit our tool, it's a big, huge tool, 3-story. And one of the fun thing here is that it's the way the EUV is generated, where you're using the CO2 drive laser, and you're creating a pre-pulse which forms we create the right target, and from the other side, tin droplets are being dropped, and you create the pre-pulse, make the right disc shape for your target, and then you have a main pulse that is hitting that tin droplet, and that generates the EUV plasma, and you collect that in a collector and send it back to the scanner for actual lithography. This is truly a I'll say it's a marvel technology. It's a huge investment. It's hundreds and millions of dollars of investment to put this tool together. But this tool is now ready for high volume manufacturing. And the first product that we will be using for 7 nanometer will use the EUV lithography. And as I was describing, we've been working on this since 2002 to show eventually our progress and show 7 nanometer chips, and then transfer the technology from our center in Albany to our manufacturing partners, and get our product chip from them for our power and Z systems. What's beyond that? So we are not on the bits part. We are not stopping that journey. We are continuing to work on what's next. FinFET, probably 2 generations of FinFET technology. What's beyond that? We're working on next device structure. What we call the device structure is the nanosheet device structure, where instead of using a single fin, now what we did was created sheets, and we came up with an optimal width and height of this nanosheet device structure, and we demonstrated in June of 2017 how can we put together 5 nanometer devices that can extend scaling beyond FinFET. And that was a very exciting moment that we were able to demonstrate that, and we were very happy to see that industry is essentially adopting this device and essentially consolidating for a few players who are left. They're trying to make sure that they can all use this device to extend the bits part of the systems, or bits part of scaling, which continue to require innovation, both in structure and the material space. Some of the work that got us to the journey, we started working on these devices in, as you can see, in early 2000. The original idea was to use the nanowire structure. Nanowire was the original concept that we were working on at Yorktown Heights, and then we scaled that structure to create a stacked nanowire structure. But then we quickly realized that stacked nanowire structure, yes, it's great fundamentally from electrostatic point of view, but it was not going to give you the performance you need per footprint, because at the end, what it matters, people don't care what you put in the silicon, but for a given silicon area, you want better performance, higher density, and lower power. So we understood that. We understood from a product requirement point of view, how do you change the nanowire or stacked nanowire structure into the stacked nanosheet structure, so that for a given footprint of silicon area, you can get higher performance and better electrostatic. Because now, instead of controlling your geometry by lithography, you're controlling your electrostatic geometry or the thickness of the sheet by epitaxy. And if you as you understand that, hey, if you use epitaxy, the process control can be of the order of atomic layers rather than a lithography where you're actually printing and etching. So this is a fantastic device structure, and we are also very happy that our partner, Samsung, announced that this will be the structure that they will use for manufacturing 3 nanometer technology that hopefully we will use for our product, as well as the industry and the ecosystem will use to continue to push the era of bits. And we have several more ideas in the pipeline. What's going on with what we have to do for device structure beyond nanosheet. We're working on those structures as well, as I described earlier or mentioned earlier on. We're working on 2 nanometer and 1 nanometer technology. That train has significant investment, and that train will continue. It's hard, it's slow, it's a lot of innovation, few companies in the field, but we are proud that we are able to have the right level of investment and the talent so that we can continue to drive that train as long as that train can keep going. So that was my first part, and I wanted to make sure that people understand that the journey around bits is still very important. We have to continue to find a way to push the CMOS scaling. There are many, many innovations that are in the pipeline, and that industry just keeps going. And that continues to be the foundation for all of the, I'll say, the AI systems that currently focus on the software side. A lot of people think AI is all about software. Well, because that's the hardware that exists is the hardware that was meant for something else. It was meant for transaction processing. And we are using software developing. That's great that we are developing new algorithm, new application, using the hardware which was meant for something else. Now comes the next part of this beautiful idea is like, okay, so what do we do in the hardware space? And how can we now start to combine the two ideas, one idea around bits and another idea around the neuron, which is inspired from the biology or the biology plus information. So I mentioned this earlier on, the idea around understanding microstructure of brain has been around for a long time. The combination of combining both bits and inspiration from brain is now happening, and you need both. You can't just build an AI hardware without having a good foundational CMOS technology, but at the same time, understanding that CMOS technology was not originally designed for, let's say, brain-inspired computing or computing which is really using algorithms which are different than what we used to use for spreadsheets and banking and calculation and airline reservations, etc. So let me get into now AI, IBM's view of AI. How do we see AI, being? Because I know AI is a term which is completely confusing, and everyone has its own meaning. Somebody thinks AI means general AI, which is sci-fi, and other people think AI means essentially recognizing face and cats and those smaller tasks. So what we did was we classified AI into three categories, three broad categories. We say where we are today is what we call that as a narrow AI, where which is deep learning is the, I'll say it's the most popular method or use of machine learning, which has really taken off, and there are certain cases where deep learning algorithms are getting better than the, I'll say, superhuman capability or better than what human can do, for instance, in image recognition or speech recognition. So this is great, but this narrow AI can do a great single task in single domain, and also it requires huge amount of data. Yes, there is a lot of data that's available, but that data that's available is not structured, it's not labeled, and it's just very difficult. If anybody who actually tries to use this data, you'll find that you're spending 80% of your time just converting that data into a format that is usable, and then you spend 20% of the time actually processing and learning from that data. That's the little secret that we won't realize that, yes, data is there, but data is not usable in the form that's available right now. The other extreme is general AI, which I will say is, it's way out there, and IBM did a sampling of leaders in AI and asked, okay, when do you think general AI may be available? And I think on an average, scientists wrote down beyond 2050. And as you know, if somebody writes down beyond 2050, that means they have no idea what's going on. They just put down some number out there, and then let's not worry about it, because that's just way out in the future. What we are focusing on, what we call is the intermediate space, which is broad AI, which is where it's basically we're doing both learning and reasoning. We are doing multitask, multi-domain, learning in one domain, applying in another domain, as well as learning from less data. That's very important because in many fields, it's very expensive, especially in the medical field, to get a lot of labeled high-quality data. That's extremely expensive. So how can we develop our model and learn from less data, but which is high-quality data? So that's the region, that's the area we are working on. And now we can start to get into, okay, how the computing is evolving and how the computing is coming together to build the AI systems. And this is some of the examples of what IBM has been doing. On the top part is, I can call it the traditional computing or the bits part of the story that we've been constantly working on. As you can see, many very powerful computers those were pushing the limits or state of the art at that point of time. The second thread here is I will say the AI thread, which is more focused on generally called software space, which is, okay, what is a new algorithm? How do you improve our models? And some of the major accomplishments, whether it's Deep Blue or playing Jeopardy, to really push the state of the art, because understanding algorithm and developing better modeling is extremely important in the space of AI. So a combination of the two essentially came together with, IBM put together, I think last year, the world's most powerful AI system, which essentially uses the technology which is based on the bits, that is using the most powerful 14 nanometer SOI technology, but combining the learning and combining some of the most advanced algorithms so that we can create, one of the things that IBM likes to do is we try to go for this big grand challenge so that we can really push the state of the art and really understand what is possible. We call this as the Formula One of computers, basically. It's very expensive computer, but this computer really helped us to, understand what are the limits, what are the knobs that we have to turn so that this computer eventually becomes, yes, it was built for the government national labs, but hey, now let's work on technology that can become more affordable. What's the next incarnation of Moore's law so that such computer can be made more affordable and put inside a pocket rather than only in the national labs. So clearly, as you can see, this is a very powerful computer, but one of the biggest challenge with this computer is the energy consumption. This Summit computer consumes 15 megawatt of energy, this one computer. That's the energy required to essentially light the entire village. So clearly that's something that is great. It's great demonstration, but it is something that is not practical. And this is the fun part. This is the great thing about we as a scientist and engineer. Hey, now let's go figure that out. How can we go work on making this system or this level of accomplishment more feasible and more real, so that the common, it can become scalable, and a lot of us can use it other than the national labs where we are starting these type of activities. To give you example of that was a very, one extreme example. Another example, even in the space of narrow AI, when you are using some standard data sets like ImageNet set using a standard network model, for training these type of data sets, it needs 4 GPUs, 16 days, and 385 kilowatt of power. So clearly, that's great. That can be demonstrated. That's all we got right now. So we are using it. But this has some problem that this is not a scalable AI system. And now our journey is, okay, so what do we do? Where do we go from here? So from IBM, we always believe, we really believe in collaborative research. We believe in bringing community together because we know so much ourselves, bringing all the partners together, its commercial partners, academic partner, and realizing that we had generated enough knowledge inside our company, and there is enough knowledge exist in the society that we can really bring it all together. And we launched earlier this year AI Hardware Research Center. It's headquartered here in Albany, New York, and we have, in addition to Albany, we have 4 labs participating in this research with us. 2 labs in the US, Watson Lab as well as Almaden Lab, and then we have Zurich Lab and Tokyo Lab. Each labs are focusing on one aspect of this broader AI research agenda that we're trying to drive through this AI Hardware Research Center. And this has many collaborators from industry as well as academic. And we'll find a path to make sure that we can do more work with MIT as well in this space of AI hardware research. And this center is focused primarily on the hardware technology. However, it's important that when we look at hardware, and that's I alluded to that when I started in the beginning, hardware by itself is not enough. Software by itself is not enough. And we are fortunate that at IBM, we are able to bring it all together by bringing in the expertise in all aspects of hardware technology. So the way we are seeing or trying to figure out and trying to push the art of hardware technology is to have a complete end-to-end stack structure. So at the bottom of this R&D is the process technology, which continues to be very important. I saw a lot of good work going on here in the materials area, integration area, which is important because as you develop new devices or new materials, we need to be able to figure out not only those material systems, but how do we integrate it, build chips from those systems. So clearly, process technology is very important. Design and architecture is also very important. You cannot develop your process technology, materials innovation and device innovation without understanding how do you build a new AI chip which can use these new devices, which is a very different area of R&D basically. Because we have never built, we have only built traditional digital chips or the ones that has been commercialized. So we are working on it. We are trying to figure out, okay, how do you build the chip architecture that can leverage some of the new devices that are being used or that are being developed in the space of new materials for AI. Third thing that is important on top of that stack is the emulation and software. What type of software adjustment that we have to do? What type of what type of instruction set? What type of essentially how do you make that chip run? And that software requirement is going to be different at the algorithm level or different part of system software level that compared to what is available in the traditional chip technology. And then finally, coming from the top, coming from the application side, which application do I want to focus on first? And let's start to understand for that application, what type of algorithms are being used most. For that algorithm, how do you accelerate? What part of acceleration you want to have first? And for that acceleration, what type of chip you want to design? And for that chip, what devices can really create that acceleration? So clearly, understanding this, if you want to really build the AI system and focus on innovating in the hardware space, then you have to look at the entire stack. And you have to have a good understanding across all of these pieces so that we can really innovate and build system which can reach to the performance that I was describing of Summit and Sierra, the Formula One performance, but the power requirement and the cost requirement need to be something that is much more scalable for broader society. So how do we go on that journey now, going from where we are? So IBM Research have put together this roadmap, which essentially, in our view, we believe that we have a path for next 10 years, that if we go on a new journey to build this AI system now, which uses both the bits, the technology that exists, that's the backbone, and the innovations on top of it, then we could get 2.5 times improvement in the compute efficiency per year. And that's needed. I'm sure you know that the requirement for AI system is even higher than that. The society is demanding almost 3.5x every 3 months. Not sure we can do that, but this is a reasonable, this is a roadmap that we believe is executable. At a high level, we broke this roadmap into 3 broad categories. One broad category is what we call digital AI cores with approximate computing, because start from innovation where it can have the fastest impact. So that innovation will be in the space of chip design and chip architecture. Step 2 would be start to introduce new material. We call that analog AI core. What it is that, okay, now we have, I'm sure at MIT, there's at IBM, there's significant work going on to develop what's the new device that can be used as the synaptic element and can start to be inspired by brain. It's not really representing brain, but can it store weight and can it simplify some of the very high power consuming calculations like matrix multiplication and accumulation. So can we how do we simplify this? How can we start to integrate those devices? But the devices for which the material system is a known system, which is very important because semiconductor industry would not adopt completely new material system very quickly. Eventually it will. Like copper, like high-K, it took time, and we went through that difficult journey ourselves. But start with the material system that is compatible with the let's say the manufacturing or the traditional semiconductor process. So that's our step 2, and the step 3 is that let's now develop the ideal material system. And yes, that ideal material system and ideal device can have difficulty of making that compatible with the traditional semiconductor fab. But hey, if we can demonstrate, step by step that this is valuable, and we can prove that in a pretty scalable way, then the industry will adopt. Industry has adopted new material system. It's a matter of showing the value proposition and understanding all the challenges. The investment in semiconductor industry is of the order of hundreds of billions of dollars, and nobody will make any change, as you know, unless there is an absolutely need to make changes. So let's start with the first part of digital acceleration. And the area that we are focusing in that space is reduced precision computing, where basically what we're doing is we're trading the numerical precision for computational efficiency. And then we are making sure that while we are doing that, we are reducing our precision so that we can get faster and low power computer done. We want to make sure that there is enough algorithmic innovation that we are not losing at the end of the day accuracy, because model accuracy is very important, and sometimes it gets lost that we can do low precision compute, but well, we are also losing the accuracy, and you got to do everything at the same accuracy as we are starting to reduce the precision. But that's a very big knob. We understand that knob. If you go, start reducing from 64-bit to 16-bit, a 2x reduction in precision can give you 4x reduction in area. That's significant reduction in power. And we've been on this journey for a long time now to understand how do you create this chip architecture, which is now truly, inspired by using the power of reduced precision, and start to get, show how much would be the utilization without losing accuracy, and start to build those chips and the systems and start to implement some of those into our systems. So we are on this journey of both, we've been publishing paper in that space for some time, since you can see since 2015, to start to show, without losing accuracy, what is the minimum number of bits that you can use for training and for inference. And as you can see, we're making systematic progress in that space. Today's system still use, a lot of AI systems use GPUs, which is bits, and which is truly optimized for some different application space. And what we're doing is, fortunately, using a clean slate and essentially designing a chip that is really made for, accelerating AI workload using reduced precision understanding from our scientific work here. And some of the most advanced training algorithms that we have been able to develop without losing accuracy is 8-bit training, which is as compared to using a traditional 32-bit floating point for the same accuracy. So clearly that's a significant, now you can start to see the significant benefit that you will get going on this journey. And on the journey on the inference side, where you can be a lot more aggressive and going as low as 4-bit or even 2-bit inference, now you're starting to get into regime that things are possible, and the amount of silicon area reduction, which translates into reduction in power or improving efficiency, is possible. So clearly that's the play that we want to have. There is significant innovation in this space. And we have published in last VLSI our digital AI core for using approximate computing as the vehicle, as a step one, because we got to look at roadmap and we have to go step by step in this journey. We can't take step 10 while we haven't figured out, okay, what's the next step? What is a 2.5x improvement? What's 4x improvement before I can go to 1000x improvement? And this is something that we are implementing, and we have had 3 rounds of demonstration, and we are starting to use this chip that essentially using low bit precision. And one of the things that we are also finding out that the traditional accelerators that we use, like GPUs, their utilization rate is also very low, of the order of 30%. Whereas one of the things that we have to push, if you go start from the ground up, then you could start to get much higher level of utilization of the order of 80 to 90%. That means you're not wasting silicon area. That means you're not wasting power. And some of the demonstration, showing that we are not losing accuracy. So going from using a 32-bit baseline, we are able to show that for 8-bit multiplication and 16-bit floating point accuracy, we are able to get very close to the same level of accuracy that is needed, or that is seen by just using the software, which generally runs on a 32-bit floating point calculators. So that was the first part, which is around chip architecture improvement. Step 2 is what can we do from an integration point of view. And the biggest challenge in the AI system is the bandwidth. How quickly, as we were talking about earlier on today, how much time you are wasting and how much energy you're losing while you're moving data back and forth. So that's the next area that requires different thinking. And just an example that the compute rate has been improving significantly in this space, like 40x in last 10 years. The bandwidth has not been improving at that rate. And what can we do as a academic and as the research community to improve bandwidth? And the idea that we are going after is essentially, you can call it heterogeneous integration idea, where we can start to work on what are the new these technologies existed, but they existed for different purpose. Now we can start to use some of the 3D technology development, like using through silicon via technology, now applying in the space where we are building 3D or AI system, combining that with the 3D chip design and system architecture to start to build the, start to essentially attack the bottleneck problem, which is essentially putting memory chip and the accelerator chip close to each other, on top of each other, with a very, very high or very low pitch and very high data rate. So that's the next, I will say, logical step beyond the accelerator that we have to work on, or we are working on. Next is the analog AI core, which is the step 2 in our journey. And some of these things take time. And we got to start all of these things in parallel. And I was very happy to see earlier today that there's a lot of work going on here at MIT in the materials research space to develop these new material system, new devices that can be used to store weights for essentially performing the eliminating what we call the von Neumann bottleneck, where essentially you're moving data back and forth between memory and the processor. And can we start to perform those compute in the memory itself, and being able to store the weights in those cross point arrays, and instead of having many cycles to perform one single matrix multiplication and accumulation, you can perform all of that in essentially one cycle. And that's a significant improvement in your, let's say, deep learning computation, or essentially which can be converted into power reduction, because now you're starting to get much higher efficiency by using the non-volatile memory element. We are at IBM are using phase change memory material for our step 1 journey. The reason we are using that material, the material has been around, the material has been used for memory application. We are converting that material system for the synaptic element application, so that we can store, instead of storing binary information, we can store more information that is needed for the AI system. This is some of the demonstration where we are able to show that in some applications where we can do the entire transfer learning using software, we are starting to replace one of the layers of this neural network using the phase change memory device and start to show the same accuracy as one would get in a 32-bit floating point software-based system. So starting to get proof point in that space. Finally, in the journey, the analog material system for storing the weight for this cross-point element or the synaptic element, I started using the material system that we know. What's the next material system? How can we make the device which was originally, which requires certain different set of criteria? IBM research had published the requirements for the device. We call this structure a RPU structure, or which essentially has certain requirements for linearity, number of states you want, drift you want. So now we're starting to work going from a typical PCM material, which was essentially designed to store two state for a memory application. How can we make that material system linear and symmetric so that you can store many, many states, as many as 1,000 states if it's possible? What type of, what new materials that are required? How can we use even some of the existing materials, like our knowledge in the space of high-K metal gate? Can we modify that system? Can we dope that system so that we can start to get much more symmetrical properties for the device element or non-volatile memory element that we want to use for for creating essentially these crossbars for matrix multiplication and accumulation function. So as you can see, we're making systematic progress. We are using RRAM-based elements to begin with and modifying that significantly so that we can get closer and closer to the symmetric property that we are looking for the application for the RPU structure that we described earlier on. So clearly, those are the two main focus areas for us, for me in particular, for my team, to figure out how do I combine the knowledge of bits and the knowledge of neuron. And on the knowledge of neuron, both starting from digital innovation to analog, analog element, where you're using the material system we know, to the ultimate analog element. And we put together this roadmap of 2.5x per year that we can show to the industry in this collaborative environment and use it for IBM system as well. The third part, which is equally important and very fascinating, but I will not be able to talk about it today in the interest of time, is the quantum computing. Clearly, that's the third pillar of computing amongst the three beautiful ideas I talked about. The part I wanted to talk today also is how do we consume this compute? So IBM bought this company called Red Hat for a very, very big price because we really believe that that's the way the society, the industry will consume compute. And what Red Hat did for us is that it provided a neutral layer. Because one of the things that people are stuck with, that if you go and start to use compute by somebody's cloud, then your applications get stuck with that cloud. And it's very difficult to move from company A to company B. And now it costs a lot of money to a lot of investment to move the application from cloud company A to cloud company B. What Red Hat does is Red Hat essentially provides a neutral layer so that any application that is developed at the top layer in the new cloud environment or cloud native environment can now be essentially transparent, and the company can use any of the cloud service provider. And if it's developed on a Red Hat OpenShift environment, then it's completely transferable from cloud to cloud. So that's great, because that's something that we really need. The industry needs a equalizing or neutralizing function so that there can be more innovation and companies are not, or the application are not stuck with one cloud provider, because that's the way the compute is going to get consumed. So the three ideas of bits, neurons, and qubits, we believe will get consumed. It's a heterogeneous fabric, which is the hybrid cloud fabric. That is the path to consume this compute. And then from there, the huge explosion of innovation in the space of software or automated programming and AI that is evolving and that will evolve. So that's the story of how we see the future of computing, how we are working on that journey, and I'm very proud that we can share it with you all, and MIT is part of this journey as well. Thank you.
Thank you very much. We can take questions now. Yes.
Hi, thank you for the talk. It was great. So 50 years ago, Mr. Armstrong landed, right, on the moon and achieved a breakthrough in American innovation. And IBM does something similar with Summit, accomplishing the world supercomputer, hitting the 500 list of the supercomputers ahead of the foreign accomplishments. In that architecture, though, it was IBM and NVIDIA, right, that together did it. The AI part was mostly an NVIDIA, which is GPU architecture. It's not necessarily neuromorphic. As far as I know, IBM also has True North, which is one of the first spiking-based neural architectures ever designed, along with HP perhaps. I wonder why it wasn't used in the Summit supercomputer.
Good.
And why it was. And you were showing us all these incredible things that are ahead of the game, but while you had it, why it wasn't in there? Thank you very much for your time.
That's great. Great question. Two parts. I will say that one of the major innovation in the time frame of Summit, it takes 10 years from the way when we bid for it and we actually built the system. At that time, it was not known how GPUs can be used to accelerate AI workload. That was the innovation there. And we worked very closely with NVIDIA, and we created a very special NVLink protocol to be able to connect CPU with NVIDIA's GPU to truly accelerate the AI workload. So the whole idea that GPUs can be used as an accelerator for AI workload didn't exist at the time when the concept of Summit was put together. So that's a great idea. We know the innovation now, and it's like, oh yeah, of course we can use GPU. But the whole idea of GPU was not known. GPU was known for graphic processing, so it was developed for graphic processing. So that was the main innovation from an idea point of view. How do you convert a traditional, I will call it bit-based system to be really superior for AI workload? So just to clarify that answer, that we were very fortunate that in partnership with NVIDIA, we were able to understand it, innovate it, and really create this value. And you can see where industry is in using that technology now. With respect to True North, True North was our first incarnation in that space. We're trying to, at that time, we're still trying to figure out what is the right way to accelerate, you can call it machine learning. And we are starting to settle. So we learned a lot in that journey, but deep learning is where our focus is, basically. If you look at a lot of workload are really using deep learning. And from the knowledge that we generated out of the True North project, we are continuing to develop newer accelerators that we described in that path to essentially focus on the deep learning workload. And that requires a different architecture. And so we made call, and we had to move forward with a commercial application on one side, whereas keep pushing the art in this scientific and research community on the other side. And you will start to see that more and more confluence of the two as we start to get more and more systems out, basically.
Any more questions? In terms of the different processing technologies. So you spoke about the different processing technologies that you develop in Albany. What level of advancement or maturity do you have to demonstrate at Albany before you go to a partner like Samsung for the gate-all-around technology, and have them either convince them or convince yourself that it's worth pursuing this? Are there performance targets that you're trying to hit, or do you show arrays of devices working at Albany? Everything. We need to have a design manual, a PDK, reliability target, performance target, yield target. So we got to get it to a very reasonable maturity level, because although the investment in Albany is already very large, but the investment in a manufacturing fab is even larger than that. So our approach is always working with partners and working in collaboration
And every project we do at Albany Nanotech always has a manufacturing partner as a collaborator. So they are working in not only, so they are working in also creation of the technology. Although IBM is the host and we drive the agenda, but our partner is like side by side with us and watching us and helping us for every project, whether it's logic project, memory project, AI project, so that we always have this manufacturing expectation in our mind. And we develop all the proof point, including a complete readiness of PDK so that they can try it out, we can try it out, because we have our own product, so we can use our own product as a test to make sure that this is a superior technology compared to prior technology. So pretty high level of maturity.
There are like reliability targets that you want to meet at Albany before.
Absolutely,
okay, gotcha.
Absolutely. You have to. I mean, reliability is, if I have to go at the end, if IBM has to sell the system which is 3-second downtime in a year, the reliability is like number one in the priority for us, basically.
Thank you.
Sure.
So you mentioned that your custom AI chips had much higher utilization than GPUs, so from 30 to 80%, which is a very impressive improvement. Do you ever have challenges with heating and power density issues with such high utilization?
Well, I will say that these chips are designed for the deep learning compute in mind, and the architecture is carefully thought about, and there is no, it's not like we're trying to fit that chip for a higher utilization. We're designing this chip for higher utilization itself. So we may have to see, but I'm not aware of any special heating problem yet for this type of architecture. So it's like designing from a clean slate rather than trying to fit something into a architecture that already existed.
We should stop at this point. Thank you again, Dr. Khare, for a very stimulating talk.
Thank you.